The slowest grade North Island College? I think this is week 4, is that right? Week 4 of control and instrumentation? Yeah. Okay, there's a few things to tell you for the people listening on the video. First thing is your course team rep is, or course rep is John Budge. So if anybody who's listening in wants contact details, I can give you them for him. You want to see him? How do I do this? I'm trying to remember how to do it. It should be possible. Scroll the camera around and zoom in. No, that was the wrong way. There we go. You want to wave again? Yeah, okay. So that's your course rep. So if you've got any issues that you don't want to tell me directly, you'd rather feed through the course rep, that's fine. John will take them on board. Secondly, there's no class next week or the week after. Next week, officially should have been a class, but I'm going to be teaching in China, so I won't be here. There will be, obviously, the video from last year, which you can still use to go through whatever you should be doing next week. Also, if you want to come into class here, the classroom's booked for you, so you can come in and you can work on your coursework or whatever by yourselves here. Probably it might be best if you sign in at reception, since I'm not here, so that if there's a fire or something, there's not going to be anybody here to take a register. So if you're signed in, at least we'll know that you're in. Although I think we're renewing the fire regulations now anyway. Right, what else was I going to tell you? I've changed the coursework hand-in date because I felt the 22nd was a bit early, considering I wasn't going to be here for the 2 weeks before that. So it's now been changed to the 29th of October. Has anybody got a problem with that? I'm really happy with that.
Okay. You have to hand it in well before that.
Well, that's fine. Obviously, the deadline is the last possible date you can hand in. You can certainly hand in before that. If you do hand in before, you probably won't get any feedback until the same time as everybody else hands in. That's mainly just because I'm not going to be here. Usually I would try and mark them up as soon as I get them, but I'm not going to be able to do that while I'm away. So you probably still have to wait 3 weeks after the deadline before you get your feedback. That's the official allowance that UHI give. I usually try and be a bit quicker than that. But... Okay, what else did I want to tell you? I think that was all. This week, I wanted to give you a choice as to what you want to do. So officially, we're meant to be doing block diagrams. I'll just recap on what we did last week, so you remember what we've done so far. First week we looked at the design process for designing controllers, yeah? The second week was the really highly mathematical week, where we looked at Laplace transforms and matrices and simultaneous equations, all trying to build up a way of writing a mathematical model for our systems. And we only looked at really 2 systems in any detail. That was the mass spring damper, which was the mechanical system, and the RLC circuit, which was the electrical system. Both of those were second-order systems. I also did a little bit on first-order systems, but we didn't really go into a huge amount of detail on them. So we mostly looked at second-order systems in week 2. And then last week, we looked at simulating the mathematical models and determining how they responded to a step. And if you remember, there was 2 different generic equations, one for the first-order system, which is k over st plus 1, and then one for the second-order system, which was k omega n squared over s squared plus 2 zeta omega n plus omega n squared. And you did a little bit of, you'll know this by the end of the term as well, you did a little bit of determining how a system would react by looking at the parameters and the numbers that you got and relating them to those terms. So remember, omega n was the natural frequency. Frequency system will oscillate at if there's no damping. Zeta was the damping ratio, which determines how much it will oscillate and what the overshoot will be. K was your gain, or in most cases loss, because we were looking at open loop systems without any gain or without any amplification. What else was there? And that S is your Laplace transform variable. We looked at how you transform from the time domain to the Laplace domain, so you can get rid of your differential equations and just end up with a nice linear equation. I think that was about it. Does everybody remember all that? All the stuff we've done? Obviously, Scott, you won't, because you weren't here, but hopefully we'll catch up. We've covered quite a lot. You've missed quite a lot, actually.
Don't worry about it.
Okay.
Much further away.
So this week, the schedule was to look at block diagrams, but they don't really come into your coursework. So I wondered if you would rather do something that's more relevant to your coursework.
Is there an
Like,
exam?
Yeah.
in the exam, yes, everything I cover is in the exam.
That's good. A very political answer.
So we'll have to see what the consensus of opinion is. I can either do block diagrams, or we can look at frequency response, which is the last two questions in your coursework,
You do that, I think so.
which concentrate in your open loop system, and then that would leave us just controllers to cover when I come back that's relevant to your coursework, and we can do block diagrams a bit nearer the exam.
Yeah.
So
Aye.
is everybody happy with that?
Yeah.
Okay, the frequency response stuff again is a little bit mathematical. There's quite a lot of stuff about complex numbers in that, whereas the block diagrams is just algebra. But you still would prefer me to do frequency response. Right, okay, so for anybody listening in, what will happen then is I'll put this week's video in the frequency response week, which I think might have been week 6. Just so as I don't have to rearrange all the notes and look at the notes, because future years I'll probably be here, so don't save me having to. So if I switch over to PC view. Okay, so this is what we should have been doing, and what I'm actually going to do is this week 6 stuff. So when you're looking for the video, I'm going to put it in the week 6 frequency analysis, and then we'll be 1 week behind when I come back and back onto block diagrams. Might actually be 2 weeks behind because I might do controllers as well before I do block diagrams. Right, is that okay then? Is that general consensus? Right, we'll just get started in that. Turn the last board a bit better.
Fair we're going to next 3 weeks. We have. With the international one. Don't do over that week. Is it? Is there classes on? Is it?
So in terms of your coursework, I would be expecting you by this stage to have at least drawn your block diagram. Is that a bit dark? Is that okay? Yeah. At least have drawn your block diagram or have a good idea of what your block diagrams really look like. Had a good look at the Excel data and possibly reduce that to maybe readings every 1 second. I know some people have actually done all this already. And then maybe even got round to importing that into MATLAB and started a little bit of work in MATLAB as well to see the response. That's the sort of stage I would kind of hope you would be at by now. Certainly you can work on it today as well. Because I'm not going to be here next week, if you get stuck next week, you're going to have to rely on each other, I guess. So, yeah. You've been quite good. I know people have been working together quite well, which is good. I like that. That's what you should be doing. Okay, so frequency analysis techniques. So what we've looked at so far is system response with step inputs. I looked at them in the time domain and then also in the Laplace domain. We might also want to see how a system responds to a sine wave input. And as I keep saying, the Tacoma Bridge Narrows is a kind of example of a more sinusoidal input that would have been put to that. It wasn't a step, it wasn't a sudden change in wind from one value to another. It was a constant wind, and that would have kind of represented an oscillation or a frequency, a wind frequency. So this frequency analysis techniques is associated with looking at how the system responds to a varying sine wave that varies in frequency from DC right up to an infinite frequency. And they do that again by modelling, because you obviously can't do that in real life. It's very difficult to do in real life, but you can do it by modelling, by getting a mathematical model of your system and then inputting a varying sine wave. So there's a few different ways of doing this. The way the background is quite easy, but the maths is a wee bit tricky. Yes. So have you heard of Bode diagrams? Or Bode plots. I call them Bode plots. I think his right name's Bode, but it looks like bodes. Just pronounce it the way I want to. Okay, so I'll just go through the PowerPoint for this, I think, this week. Okay, so the whole idea of this is you've got your mathematical model, you simulate it with a sine wave. So there's some examples of what I mean by a sort of swept frequency sine wave. So these ones are changing in amplitude as well, which isn't necessarily what you'd want to do. What you want to do is put in a fixed amplitude. So that y dimension fixed and sweep from very low frequency right up to very high frequency. And see what your system output does when you do that. Now, to do that, we need to use complex numbers. I did a bit of revision on complex numbers in week 1. So you remember there's 2 ways of representing complex numbers. You can represent it, well, there's a few ways. On an Argand diagram, which your x-axis is your real part of your number, and your y-axis is your imaginary part of your number. Maybe just do a wee bit of revision on these before we go further. Stick to an easy one here, maybe point there. And then we've got so if you want to represent that dot, that you can do it on an Argand diagram like that. That would represent the. Remember, we're thinking about phases mostly, so in fact, it probably would be like. Okay, earlier, but it seems to have gone up. There we go. But so, if I represented that by an x-coordinate plus, you remember what the form was called? What kind of complex number that is? No. Okay, that's rectangular, or your Cartesian coordinates, yeah? They're interchangeable. I think MATLAB calls it Cartesian, but you'll quite often see rectangular as the other way. So that's one way of representing the number in an imaginary number. It's terrible. I'm just going to try and recalibrate it. I don't think it's getting it was a bit off. Usually, just stay on. Make it worse. That's meant to be an X. That's a bit better. I'm not sure. Okay, the other way is by length and an angle. Yeah, so this is just a revision from what we did in week 1. So you have an angle here and a length. So you can also represent that same phasor by that. Yeah? And that's your polar coordinates. So just to remind you of that. A couple other wee things. I don't know, did I do with you that in the first week? That if you're adding complex numbers, you use them in the rectangular form. It's called polar. Okay, so plus or minus, you use rectangular form. And divide or multiply, you use polar. Do you remember how to do that?
Yes.
Yeah, okay, that's fine. I won't need to go over. So you are going to do a wee bit of division and multiplication of these numbers. I'll just wait till it takes a minute. Bless you.
Thanks.
Okay. So there's just a couple of other ways that you can represent a sine wave is using these complex numbers. So that's the amplitude, in this case peak amplitude. Anybody who's doing principles with me, you know we normally use RMS, but for control theory we use peak. And then the phase difference between, I would say a normal sine wave, although that one's shifted, a normal sine wave and the wave you're interested in. So you can see here, I don't know how clear that is because my projector's not great, but this is our system represented using complex numbers. So it's got amplitude and a phase, which will affect the input coming in here, which has an amplitude and a phase, and give us an output here, which has an amplitude and a phase. Okay. So I guess in terms of the system, this is like the transfer function, but it's in a different domain. So far you've looked at time domains and S domains, and now we're looking at frequency domain, which is what that's in. So for instance, if you were to put an input wave in like this into this system here, which has this amplitude M1 and this phase, which shift from a normal sine wave of theta 1. That's not theta, what's that, phi 1. And then what came out is very likely to be something that's changed in amplitude and also has a different phase shift. Systems often do that. You know, for instance, I don't know if you know much about op-amps, but an inverting op-amp would give you a 180-degree phase shift. A transformer wound in two different directions gives you a 180 degrees phase shift. So you can consider them as systems, and they're causing a big phase shift to an input signal, yeah? So you can expect that this is going to cause a phase shift, but it might not cause the same phase shift over a range of frequencies. So at low frequency, maybe there's no phase shift. But then when you get to very high frequencies, when all the capacitors and inductors in the circuit have more effect, maybe there's more of a phase shift at that point. It's quite good because you guys are all electrical, so I can talk about circuits. I'm not quite sure how that relates to the likes of the mechanical system, other than that you can model them the same way. But I think it makes a bit more sense in the electrical world, talking about phase shifts. I'm not sure how well that relates to mechanical stuff. Okay, so you can see here what's happened is the output waveform has a different amplitude, M0, and a different phase, which is made up of the input phase plus a shift caused by the system itself. And this amplitude is the multiplication of the input amplitude times the system's amplitude. So that's kind of like a gain term. Yeah. Okay. So we can then rewrite the system transfer function as we did, as an amplitude and an angle, which is what we're talking about there. When we talk about angles, we might be talking about radians, or we might be talking about degrees. They're pretty much interchangeable, just with a magnitude factor. Okay, so if we want to look at how our system responds in the frequency domain, what we can do is take our Laplace transformed system, so that's the one with all the S's in it, and change all the S's to a little term called J omega, where omega is frequency in radians per second, and J, what's J? Do you think?
Square root of minus 1.
Square root of minus 1, yeah. So J is your complex variable, yeah? Or your square root, well, it's not a variable, it's a constant, complex constant. Square root of minus 1. So what we do is we take the S domain system and we change all the S's to J omegas, and then we put in different values of omega and find out what the resulting amplitude and angle is. Yeah, so of course, because we're using complex numbers, we go back to complex numbers. As soon as you're working with complex numbers, you're always working with amplitudes and angles, and that's the reason for using them mainly, is because it's quite a good way of showing amplitudes and angles, just using numbers. Yeah, so that's why we use them, because not only can we find out the change in amplitude, but we can also find out what's happened to the angle, if it's shifted or not. So we've got three different ways of doing this. Now, we tend not to do it on a linear scale, because the idea is that you're changing this frequency from 0, DC, right up to very, very high frequency, infinity. Now, if you tried to plot that on a linear scale, if you imagine trying to go from 0 to, I don't know, 100,000 on an x-axis, for instance, you're not going to see small changes, say, between 1 and 10 hertz. You wouldn't see any change on your scale. You wouldn't even be able to plot it, probably, because your scale would be so small. So what we tend to use is a logarithmic scale for both the frequency, which is your x-axis on the plots, and your amplitude, which is your y-axis. And again, that's because your amplitude can vary a lot. So at very low frequencies, you might get a very high amplitude. This is the way circuits usually work. You might get, I don't know, 50 volts or something like that, if it's a high power system. And then at high frequencies, that might have gone right down to 0. I suppose you could show that on a linear scale, but one of the examples was with the radar I used to work with. We used to always use a decibel scale, because if you were looking at something really far in the distance, it came back as a tiny signal, only microvolts of signal. But if you're looking at something really close, that would be in the tens of volts. So you couldn't plot both of those on the same y-axis. So you use a logarithmic scale all the time. So it's really just a way of expanding a scale so you can see variations, yeah? It's nothing really complicated. And of course you can do it manually as well, but it's very time consuming to do the calculations manually. I will show you how to do them manually because I think your coursework asks you to do them manually. But if you do them manually, what you would normally do is pick some frequencies and just work it out at specific frequencies. You wouldn't try and do it over a whole range from 0 to very, very high numbers. Okay, so there's an example of a Bode plot. This is the one I use the most because it's more common to electronics as well as control theory, or a Bode plot, I think they call them, to be honest. So you've got two different graphs, which is quite nice because it separates amplitude and angle, which is quite nice and tidy. So you can see along here, we've got a frequency scale that goes from 0.1 radians per second up to 100 radians per second. And along this side, we've got an amplitude scale. I don't know if you can see that very well, but that is actually 20 times the log of the actual amplitude. So flicking back, it would be 20 times the log of this. Yeah. And that's how you convert from a linear scale to a logarithmic scale for things like voltages. It's 20 log of the value. And then the phase scale, same frequency axis, and they're usually plotted like this, one above the other, so that you can quite easily line up what's happening at different frequencies. And then this scale here is in degrees, and that's just a normal linear scale. It goes from 0 to minus 90. It might go to minus 180. That's more common. So you can pick a frequency point, say maybe 1 radians per second, and you can go up here and you can see that your system has caused a phase shift of around about minus 30 degrees, and it's caused an amplitude change of maybe minus 7 decibels. This first number here is minus 6. Yeah? And that tells you what the system's doing with that particular input, that sine wave input. Yeah? Does this make sense? Oh, no, okay. So generally we tend to use a computer to do these, and MATLAB's fantastic at doing these. I can show you on MATLAB. I'll show you that after, or maybe I'll show you it now. So I don't know, we can define a system. I'm just going to make one up. I don't know what sort of Bode plot it will have, but trying to remember how you do this. I think that's a common there. Okay, so if I run that, I forgot to put the first bracket in there.
Put a normal bracket.
Yeah, I forgot to put the first square bracket in. So do a bracket there. Okay, so I've just defined a transfer function. See, I did that, just type that in. So you can get used to doing this yourselves. We talked about poles and zeros last week, I think, didn't we? And pole zero diagrams. So what's the system got in terms of poles? How many poles has it got? One pole, defined by the denominator. So it would have a pole at minus 4?
Yeah.
Yeah, what about zeros?
1.
1, 0 at? Minus 5, yeah. Okay, so actually they relate to the points on the frequency graph. Switching back to this frequency graph. I won't bother you. They relate to these points where the slopes start to change. Yeah. So in fact, that point there would be a pole. But anyway, and a 0 would cause a slope going up the way. But we'll talk about that in a minute. Let me show you how to do this. So I can do a Bode plot of this system if I just type in Bode G. I think that should work. No idea what it's going to look like. Probably a straight line since I've got one pole and 1 0. Okay, it's not a straight line, that's fine. Okay, so that was just a completely random function, but here you can see how it's done the Bode diagram really quickly for me. This is the amplitude, and that's the phase. I just wanted to show you that. We'll do a bit more on MATLAB later on, but just while I was on that page anyway. Okay, so we're going to look at some simple functions to start with, some simple systems rather. So we've got, first of all, a system with just a single 0. So that's just a denominator. There's no numerator there. So replacing the s with j omega, like I said to do, and then looking at what happens to the function as omega is put to different frequencies. So we can start by making omega 0, which is effectively DC. So that's not putting a sine wave into the system at all, that's just putting a DC signal in. If you make omega 0, then you end up with this function just being equal to A. Okay, so we could work out the amplitude of that system just by doing 20 log of A. And there's no phase shift there because we've got no imaginary part. Yeah? If you only have a real part, you have a 0-degree phase shift with a complex number. Does that make sense? Yeah. So that's along the x-axis, essentially. And then if you go into high frequencies, so we're making omega much, much bigger than A. So saying that maybe omega's, I don't know, 100,000 radians per second or something like that. It's very unlikely A would be anything like that sort of number. So A kind of disappears in the equation then, and you're just left with the j omega part. And if you convert that to your complex numbers, that gives you a magnitude of omega and an angle of 90 degrees. Because referring back to our Argand diagrams, anything that just has a j term is along the y-axis, yeah? Do you want me to show you that? Just switch back to that if you want. Yeah, so anything that's just got a j term is just going to be on this axis here. So it's obviously got a phase shift of 90 degrees. Yeah? Okay. And then at the frequency where omega is actually equal to A. So this is called our low frequency approximation, and this is our high frequency approximation. And if you make omega equals A, they actually become equal. Okay. So what you find out is when, for that particular function, okay, for this particular system where your system's defined by S plus A, that's your Laplace transform of your system, at low frequencies, you've just got a straight line, which has this amplitude. At the point where omega equals A, in this case, this will start to rise because it's a 0. Okay, so it starts to rise with an increase of 6 decibels every time the frequency is doubled. And of course, you could actually work that out. If you go back to here, you could have put in different values of omega, and you would actually get an answer here if you had real numbers. And you could plot that manually, plot by plot, and you would see what would be happening. But you can just believe me that when you have a 0 system with just a 0, it'll start to rise, and it'll rise, we normally use this term, 20 decibels every time the frequency goes up by 10. Okay, so going back to our plot here, if your amplitude was minus 24, then it would be up to minus 4 by the time you got to this frequency here, 10. Yeah, that makes sense? So you might be asked to plot these sort of things in an exam, so you do need to understand this stuff. But you're going to do it in your coursework, which will help as well. There's a picture of it. And the other thing that's a bit more complicated is the frequency. The system will also start to cause a phase change right back from 0.1 times the frequency A right up to 10 times the frequency equal to A. A is called your break frequency. So that's the point at which, if I go on to the next one, that's the break frequency there, okay, A. You can see here we've got a straight line up until that point. This is an approximation. What it would actually do, if you plotted it using MATLAB, you would actually get a wee curve starting maybe about there. But this is good enough for finding out what your system's actually going to do with a frequency input. So at this point A, where omega equals A, you've got your breakpoint, and then you've got your 20 dB per decade rise. Below A, you've got no change in amplitude, essentially, so it's nice and flat. And what's actually happening with the phase is at 0.1 times A, so a tenth of this frequency, you start to get a rise of 45 degrees per decade. And that carries on right up until 10 times this frequency. Does that kind of make sense? Yeah, if you look at the graphs, that's exactly what you'll get with a 0A. You'll get these graphs. Obviously, you'd have numbers here if you have a value for A, but yeah? So again, if you look at that and you could say, well, what's going to happen at 100 times A, say A was 1, what's going to happen at 100 radians per second? Oh, I'm going to have a phase change of 90 degrees, and my amplitude's going to be increased by 36 plus 20 log A or whatever. Yeah, so you could work out what the system was going to do at that particular frequency. That's the whole point of doing this analysis. Yeah, does that make sense? So if I go back, so you can do the same thing for poles, and in fact we're usually more interested in poles because most systems have more poles than zeros. Systems tend not to have a lot of zeros, that would make them unstable. So most systems have more poles. And the same thing happens with a pole. The only difference is obviously your pole is on your denominator of your transfer function. But the same idea, you have a breakpoint A, which will be a real number for a real system, and at that point the gain starts to drop off by 20 decibels per decade. And at 10th of that frequency A, the phase starts to change by 45 degrees per decade from 0 phase change here, right up to 10 times A. Okay? So, and this graph here is showing this normalized because it's showing frequency over A. So, of course, 1 would be A, 10 would be 10A, 0.1 would be 0.1A. That's all that means there. That's the only reason it's done like that. So, in summary, every pole gives a break frequency at the pole point, and your graph slopes, your magnitude graph slopes by 20 dBs per decade. Every 0 causes a slope of 20 dB per decade in the opposite direction, going up the way, and then you've got your phase changes there as well. And this bit at the bottom is quite important. Poles and zeros have a cumulative effect. So if you were to switch back to that, if you had another pole, say you had another brackets term, S plus B, on the bottom here, and your B pole was maybe, I don't know, 9 radians per second, or normalized to 9, you would get another pole happening here, and this would then start to go down at minus 40. So I have got some graphs showing that anyway, but so they add together, and they increase the rate of change each time, yeah? Which is quite complicated when you look to your phase diagrams to work out, but it's easier with the amplitude ones. Okay, so there's an example. I'm not going to ask you to sketch this because it's not easy to sketch without graph paper, but we'll start off with this one. So, let me start. Robert, what's the pole break frequency? Sorry, what's the zero break frequency of this system?
-3.
Yeah, good. I'll write these down. So we've got a 0 omega equals -3. Yeah? Okay, poles?
-1 and -2.
Yeah, okay, good. -1, -2. Any others? There's one more.
0.
0, yeah. That's relate to that with that. Okay? So when S is 0, we also have a pole. So we've got 3 poles. So we would actually expect this magnitude graph to be sloping up what slope per decade? With 3 poles? Ignore the 0 for the moment.
60.
60. So it'll be dropping at -60 per decade. But this 0 will prevent that, so it will probably drop at -40 per decade. It does depend where they are and whether they're still having an effect at that stage. Okay, but we don't know K, so I'm not terribly sure how we're going to plot that. Maybe just assume K is 1. That makes sense. Everybody understand that okay so far? Yeah? Right, I'll show you the plot then. There's the answer, which you got, which is good. So we're going to start with K equals 1. And it says here the effect of K just moves the whole graph up and down. So if we go back to a graph, if you change the gain, it just means that this point will go up. So the whole graph will either go up, or if it's a low gain, it'll go down. Yeah. So we can ignore the gain for the moment. Okay. So what the book's done, I think the stuff's in the book, is it's summarised the effect of each pole on the gain and the phase. So starting by looking at the magnitude, which is the same as gain, it's saying that there's an initial pole at 0, So even by the time we get to 0.1 radians per second, we're already going down at minus 20 decibels per decade at that point. And then we've got another pole at minus 1, which is going to cause another minus 20. Another one at minus 2, which is going to cause another minus 20. Oh, sorry, what's that saying? Oh, that's just the effect of this pole. Okay, I'm not sure what that's actually saying, to be honest. Oh, that's at the... Sorry, right, okay, so this is the frequencies along the top here, and this is the poles and zeros being added in. So the first one, at 0.1 radians per second, we've already got a slope of minus 20 because of the pole at 0. And then at 1, we've got a new pole just starting there, that will add another minus 20. 2, we've got another pole starting there, which will add another minus 20. And then at 3 radians per second, that's where the 0 occurs. So I would have thought that should have said plus 20 there, actually. I think that's a mistake. But anyway, adding them up, it's right at the bottom. So initially, at low frequencies, we've only got minus 20 dB per decade. But then once we get above 1 radian per second, the drop's going to be more. It's going to be minus 40. At 2, it's going to be minus 60. It's probably easier just to show you the graph. And at this point, the 0 is going to have an effect and negate minus 20 of that. So it'll not drop so steeply, but once it gets to 3, it'll drop at minus 40, I think. I did try and draw that. It's not possibly very well drawn, but hopefully you're able to see it. So this slope here is due to the pole at 0. This slope here is due to the pole at minus 1. This slope here is due to the pole at minus 2. And then you can see here it's gone back to being more like that. And that's due to the 0 at minus 3. Does that make sense? Yeah. They're quite difficult.
What do you mean it's due to 0? Like?
What's that?
It's due to 0. How does it change? This is due to 0 at minus 3. How come it's plus 20 then?
Because of the 0 on the top line. So going back to every pole gives a minus 20, every 0 gives a plus 20.
Oh, right, yeah.
So that cancels out one of those.
Yeah, cool.
Yeah, good. That's good if you ask questions because it means you're actually listening as opposed to just sleeping. Right, okay, so that would be a magnitude plot. The magnitude plots aren't too bad. Trying to do this in a phase plot of this would be actually very difficult to do manually because obviously the pole at 0 is going to have an effect. You can't really get 1/10 of 0, but it's going to be already minus 45 degrees down by the time you get to 0. And then it's going to have still be minus 45 by the time you get to this 1. And then that's going to have an effect as well from 0.1 up to 10. So they all overlap each other, and it does get really, really difficult to plot phase. So I don't think I've done a phase. They've tried to summarize it here, but I don't think I've actually done the plot. So that minus 45 is due to the pole that's minus 1. Pole minus 1? Why have they not done the 0? I'm not sure why they've not done the 0 there. I think we'll skip over that because I don't think you'll be asked to do that. If you're doing this, you'll be doing it in MATLAB. You won't be doing it manually. It's way too difficult to do. Oh, right, there we go. They have actually tried to do it, but yeah. So this point, the fact that that's gone down to minus 90 is due to the pole at 0, and then that's it carrying on up until the next pole. Then it gets steeper. So that's 1/10 of the next pole. That must be 1/10 of the 0. But the pole's still having an effect there, and then so on. It's really complicated. I don't think we'll worry too much about that. Okay, so you can use these bode plots to determine whether your system's stable. What do I mean by stable? What does an unstable system do? Yeah, oscillates continuously and probably eventually breaks. So that's unstable. In fact, to be honest, a stable that oscillates continuously at the same amplitude is a critically stable system. But a system that the amplitude builds as you put the input in, that would be an unstable system. But yeah, quite right. Stable system. So it's quite important to know whether our system's stable or not at a range of frequencies. Because we don't want, for instance, a damper on a car if you go over a particular level of bumps, you don't want the car to bounce bigger and bigger and bigger until your shock absorbers break, yeah? So you want to be able to do this. So the definition of stability is that you have negative feedback if the gain of the feedback is greater than 1, or if the gain of the whole closed loop system is greater than 1, the feedback has to be still negative. And you can write that in terms of mathematics by saying that you have to have a gain of less than 1, which equates to 0 decibels. If you do 20 log 10 1, you'll get 20 log 10 1, you'll get 0 decibels. So that relates to a gain of 0, a gain of 1, and this relates to a phase change from negative to positive feedback. Yeah. Do you imagine if you're putting a wave same like that? Go back to here. So for this to be stable, that has to be negative feedback. Yeah? So if you're putting a sine wave in here, and by the time this all comes back, you get another sine wave that's in phase with that. Sorry, no, 180 degrees out of phase. I don't know if I've drawn that very well, but it's 180 degrees out of phase. And then you then subtract that. What you're actually going to end up doing is flipping this over and then adding it. So you end up with positive feedback. Yeah. So it's okay if the gain's really low, because what you're adding will be very small. But if the gain's 1 or greater than 1, you're essentially going to be adding the same size of wave to the one you're putting in, and obviously that's going to make your output much bigger, and it's going to make it unstable. So that's what that criteria is defining, that you still have negative feedback. You don't need to remember that, that's just trying to illustrate why that's important, or why it means what it means. Okay, so what we've got, if we've got our Bode plot, we can actually work out whether we have a stable system, and we can also work out, can we add more gain to the system? Maybe our output's a bit small, we want it a bit bigger. Can we add more gain without making it unstable? Can we add more phase shift without making it unstable? So we've got two terms here. We've got a term called the gain margin, which is the amount of gain you can add before it becomes unstable. Or you've got also a term called the phase margin, which is the amount of phase shift. So I don't know, if you had a system and you maybe wanted to change a sensor on it, you might want to check that it's still going to be stable. If you buy a sensor that gives you a bigger output, or a sensor that gives you more of a phase shift. So it's useful to know how much more phase shift you can add and how much more gain you can add to the system. And you can measure them on the Bode plot quite easily. So obviously with the gain margin, if the system becomes unstable at 0 decibels and a minus 180 degree phase shift, the gain margin is going to be the amount of extra gain you can add before you reach that point. And the phase margin is going to be the amount of extra phase you can change before you reach that point. And you can read them on the Bode plot quite easily. So for instance, if you had a Bode plot that did something like this. So the interesting points are 0 decibels and minus 180 on your y-axis, yeah? Looking back at your graphs. So the points that we're interested in are the points that correspond to those two conditions. So if, for instance, your magnitude plot did something like this, this here is the point at which the phase shift has reached minus 180, yeah? So remembering that these are frequency axes, and they're both the same frequency axis. So this would be the frequency in radians per second at which the phase shift has become 180 degrees. So that's your minus 180 degree point. So you could actually add this much gain. So you could shift the entire graph up by that much gain before it would become unstable. Now you wouldn't want to do that. You wouldn't want to shift it so that that was on that point. But it just gives you a measure of how much you could shift it by theoretically. Obviously, you don't want it actually at that point because environmental factors might play a part, gains might change, and then you could end up with an unstable system. But anyway, so does that make sense? Can you see that okay? Yeah? And then the same applies with the phase shift. So with this particular system, we have a phase round about a lot less than minus 180, a phase shift here, maybe minus 90, minus 20, I don't know, whatever that reads, at the point where the gain has dropped to 0. Yeah, so like I said, gain normally drops because there's normally more poles in your system. So at the point where the gain's dropped down to 0 or times 1, the phase shift is a good bit more than minus 180, sorry, a good bit less than minus 180. So you could actually change that phase of that system right down to this point here before it would be unstable. So that's called the phase margin. It's how much you can shift. So it's how much you can shift this graph up and how much you can shift this one down before you reach the two conditions where 0 and minus 180 correspond at the same frequency. Yeah? So it's a bit complicated, this stuff, but hopefully you'll get the hang of it when you do it yourself. Okay, so here's another example. In this case, h is just 1, so we don't need to worry about plotting GH. Normally you do plot GH, but h here is just unity feedback. So there's no transfer function in the feedback path. So you can see here, this system's got how many poles? 3, okay, and they're at minus 2, minus 4, and minus 5. It's also got a gain term of 200. So our straight line point on the graph would be 20 log 200, whatever that works out as. And then it will start to, the gain or magnitude will start to drop at 2 radians per second, 4 radians per second, and 5 radians per second by different amounts. Okay, so there's no real reason to multiply that out, I don't think, because, oh yes there is, because it gives us our low frequency point. Okay, so I said to you, normally you change it to j omega, but you can do it with s as well. But ignoring this slide, what we've really done here is made all the s's equal to j omega, and then we've made omega equal to 0. So you can see when omega is 0, that term will disappear, this term will disappear, and this term will disappear, and you're just left with 200 over 40. Yeah? And that gives us our gain at DC frequencies. S tends to 0 is DC, or j omega tends to 0 is DC, of 20 log 10 of that, which worked out as 14 decibels. And then we know the breakpoints, we've already talked about them. So the first breakpoint is going to give us minus 20 dBs per decade, then minus 40, then minus 60. That makes sense okay? Everybody still following? Yeah, good. So if we plot that, again, it's not terribly clear, but this here is our 14 dB, I think, straight line. And then you can look at these on your own later. And then this will be the first pole, which was at, I've got 2, 4, and 5. So that'll be the first pole at 2. And then the slope increases at 5. And then by the time you get to, 4. And then by the time you get to 5, yeah, it's going down at minus 60 dBs per decade. Okay, so now we can measure phase gain and phase margin for that. And I know it's not a very clear graph, but like I say, you can have a look at it later. But what you can actually see here is the phase shifts due to these poles. Yeah. So the first one starting at 0.2, and then another phase shift coming in at 0.4, and then a final phase shift coming in at 0.5, giving you this very steep slope here. That actually crosses minus 180 at this point here. Maybe it's better if I actually drawn it. Let's see it better. And then just using the mouse. Okay, so for that system, the minus 180 points there, that corresponds to minus 180 on the graph. So we can look up at that frequency, whatever that is, and we can see at that point our gain is here. Okay. Now 0 decibels is this point here, so that corresponds to that line. So our actual gain margin is how much we could shift that dot up to 0. Does that make sense? Yeah, so it ends up being that amount there. And then you can do the same with the gain, with the phase margin. So the point at which this magnitude graph crosses 0 is at that point, I think. Yeah, it's this point here. So looking down at the same frequency, that corresponds to that phase shift there. And so you can see that we could actually shift the bottom graph down by this amount. Colours are meaningless, by the way. Probably should have done it more colour-coded, but you can shift that down by that amount. And then that then tells us that we have a gain margin of 4 decibels and a phase margin of 10 degrees. So that's how much additional gain and phase shift we could add to our system. Do you think that would be a stable system?
Stable.
It is stable as it stands, but it's not good. It hasn't got a lot of gain margin, it hasn't got a lot of phase margin. You can imagine that over a temperature range or over a variety of input changes or whatever, that's not a lot of gain margin, 4 decibels. So you would probably be pretty close to critical stability with a system like this, because you don't have enough gain margin, enough phase margin to cope with the conditions for a real system, where things are changing a little bit all the time. So that's not really enough gain margin or phase margin, but it is stable. Okay. So these are what we'd normally look for an electrical system. I'm not sure with a mechanical one. You'd normally be looking for a gain margin of at least 10 decibels and a phase margin of 45 degrees. That's to cope with things like power supply changes, component tolerances, changes over temperature, things like that, yeah? So you wouldn't really want to design a system with a smaller gain margin and phase margin as the previous slide. And what they define that is marginally stable. So it is stable, but it wouldn't take much to make it unstable. Okay? Happy with that? I'll carry on. Yes. Any questions so far? I've done quite a lot. Okay, now there's 2 more kinds of plots. If you don't like Bezier plots, there's 2 more plots you can use to get this gain and phase margin measurements from. I think the next one's a Nyquist one, which is a really hard one to understand. But yeah. I think in terms of Nyquist, I wouldn't worry too much about the theory about how the Nyquist plot works, but just be able to read the plots. So there's a bit in the slides about the theory, but we're not too bothered about theory. But in terms of how it works, you start with it's like an Argand diagram, essentially. So we're showing amplitude and phase, and we're sweeping a phasor round this circle, starting with when our frequency is 0, we're along the x-axis, so we only have a real part of the system. And then as our frequency goes up, we get round to this point where we only have an imaginary part in our system. Yeah, so that's similar to what I was telling you before. The slightly odd thing is it's a negative sweep rather than a positive one, but that's just the way they do it. So instead of plus 90, it's minus 90. That omega equals infinity, effectively. So, any point along here, this shows you the different frequencies. That's at 1 radian per second. This would be the phasor at 3 radians per second. So remembering that the phasors are coming down in our arrows there. Okay, now what we want to do is we want to determine the stability of our closed loop entire system. And the Nyquist and Bezier plots both do that by looking at the equivalent open loop system, which is just G times H. If you go back to, probably if we'd done the block diagram theory, it might have made more sense. But if we go back to our drawing here, if you're just looking at G times H, that's not the transfer function of that system, is it really? Because did I show you that the transfer function is G over 1 plus GH? No, I probably didn't, because I think that was the one we were meant to be doing this week. Okay, so the transfer function of this actual system, and I'll show you this when we do the block diagrams, but what you actually end up with is 1 plus 1 G over 1 plus GH. So you could redraw that system as a single block. And that's exactly equivalent to that. Yeah? So you don't need to worry too much about how we get to that, because we will look at that later. So obviously, if we're just looking at GH, that's not the transfer function of our system. That's the equivalent open loop transfer function. So all these frequency plots are all done using just that term there. But they still tell you how the closed loop system is going to respond. I know it's a bit difficult to understand that, but the reason they do that, the Nyquist theory or Nyquist plot kind of explains it a little bit. Does that make sense? Understand what I'm talking about there? That just multiplying G times H doesn't give you the full transfer function of that? Yeah? Okay, if you don't understand, you just have to believe me for the moment. We'll see about it next. And we'll do that. Okay, so what we're actually plotting on this diagram is GH, not G over 1 plus GH. And because of that, the poles and zeros don't exactly correspond to the poles and zeros of our actual system. But what you find is that if you plot GH, then the zeros of GH, never mind the 1 plus bit there, the zeros are actually the poles of the closed loop system, and the poles are the poles of the system. So you don't need to be able to do the proof of that, but just believe me. We'll also miss that as well, because that's on about plotting, but that's just basically showing you the difference between a stable and unstable system. So, these are zeros, but they become poles of the closed loop system, so that would be a stable system. And this would be an unstable system because these zeros would become poles and they'd be in the right-hand plane. Did I tell you about that last week? About stability being the left-hand plane? Mm. Okay, right. Well, don't worry too much about that just now, remember. We'll also just skip that for a moment. I don't want to make this too difficult for you. So that's just explaining how this plot works. So at low frequencies, the j omega term disappears, essentially, and you end up with just a straightforward k over a term and an angle of 0, because it's only a real number. K over a is a real number. And then at high frequencies, the j omega part becomes really big, so you end up with just k over j omega, which tends to 0, because j omega is really big. If you divide by a really big number, you start to get towards 0. So that tends to 0, and your phase shift is actually minus 90 because omega's on the bottom line. Yeah? So omega's got, that term's got a phase shift of plus 90, but when you divide by plus 90, you know if it's a denominator, you then subtract. So it actually becomes a phase shift of minus 90. I don't know why that's so plus there. So looking at that on the diagram, it looks really complicated, but it's actually not that bad. So this is the phasor that we're plotting while we're doing these diagrams. And we're starting with omega equals 0, so your phasor would be here. Don't draw on that. That would be the phasor when the frequency equals 0. There's not much to go, guys, honestly. And this is quite tough. Right, so when omega 0, that would be a phasor there, which would be on your real axis, yeah? For the one with shore area, that would be k over a, yeah, amplitude. So the length of that phasor would be k over a, the diagram we had before. And then what we're just going to do is increase the frequency going around that way. So, you might have 1 radian per second, 10 radians per second, 100, and so on, around that way. And watch what the phasor does as we do that. So what it's going to do is it's going to change in amplitude, and it's also going to change in phase shift, obviously, as well, as the imaginary part gets bigger. Because that was our function, yeah? So you can work out the gain and phase margin from this graph as well, because at the frequency at which the amplitude of that, or length of that phasor becomes 1, that's equivalent to a 0 decibel crossing point, yeah? So that green is equal to 0 dBs. And obviously, when it gets to if that one's done that. When it gets to that point, that's when you've got no real term, when you've got your minus 180 degree phase shift, yeah? So if that was its phasor at 0, frequency 0, by the time you get round here, that's minus 180 degrees. So you've had your minus 180 phase shift. So the point of stability or instability would be crossing that line at minus 1. Because that minus 1 there represents 0 dBs and minus 180 degrees. Yeah? So measuring from there, we can measure the phase margin very easily. The phase margin is just that. So that's how much we could sweep that amplitude 1 phasor around before it crossed this point. Yeah? Makes sense? And the gain margin is actually, what you measure on the graph is 1 over A. I'm not sure how that works. It's to do with division. It's to do with the fact you've got the division there. So what you're measuring is 1 over A, but the gain margin is actually 20 log 10A. Okay, so say you measured 0.5 there. At that point, just as an example, if that one point was 0.5, then your gain margin would be 20 log of 5. Okay? But it's all related to that minus 1 crossing point at minus 180. So that's another graph. For some reason, control theory people seem to like this graph. Electronics people and electrical people prefer the Bode diagrams. But they both tell you the same thing. I'll just show you how you do that on MATLAB, just when we break from the maths for a minute. So, you just type in Nyquist G, and hopefully it should come up with a plot. Yeah. To me, that doesn't really tell you very much, but there you go. This system's totally stable because it doesn't go anywhere near the minus 1 point. You can see this little red cross here tells you the instability point. Yeah, so I don't know, that system's a bit of a weird system. You get the idea, hopefully. And then there is one more type of plot. So that's the Nyquist plots. The Bode ones are probably more useful, in my opinion. And then finally, we'll not do that, I don't think. I think we'll miss that out, because I think you've had enough maths, am I right? You can come back to this yourselves later. Or do you want me to go through it? Should I just go through it anyway? What do you think? Well, you can always look at the video later if you really want just now, can't you? Yeah, I think I will just go through it. I know some people are struggling, but... Okay, so for this system, we're trying to find out what value of gain we can have here before the system becomes unstable, yeah? And we've got 3 poles on the bottom, I think, which is the same as the previous system. So, initially, we'll just assume that the gain's 1. We're actually going to try and find a value of k maximum, but we're going to assume it's 1. Just to remind you, j is actually the square root of minus 1, which isn't a real number, but if you square j, you get minus 1. The square root of minus 1 times square root of minus 1 gives you minus 1. So that's just a wee bit of maths theory there. We've multiplied out the denominator, so just multiplying, using your Boyle type laws to get this denominator here, and then we've replaced all the s's with j omegas. Okay, so the first thing to do is find out what happens when the input frequency is 0, which is nice and easy, 0 radians per second. Just make all the omegas 0, and you get left with 1 over 48. So that's our magnitude, and in fact there's no angle there anyway. And then if we make omega infinity, we get 0, yeah, because 1 over infinity gives us 0, and the angle will obviously be 90. In fact, actually minus 90, so these slides are wrong. I need to correct that. That should be minus 90. Okay, what have we done now? Okay, so now we've changed it to being just looking at real and imaginary parts. So this term here becomes a real number, because j squared, you've got a j squared omega squared, so j squared becomes minus 1. So that just becomes a real number. This is still an imaginary number, and that's still an imaginary number. So we can work out what we're working out there. What the frequency is when the system crosses the negative real axis. Okay, so it will cross a negative real axis when this omega is big enough. Does that make sense? Go back to what we're doing there. Yeah, we're trying to figure out what frequency it crosses this axis at. So it's going to do that when the imaginary part disappears, yeah? So you've got minus omega 3 plus 44j omega. So that comes from this term here. And we want that to disappear because that's the imaginary part. And obviously if you're... Obviously if you're crossing a real axis, there's no imaginary numbers involved, yeah? There's no j part involved on that axis there. So we're trying to find out what value omega is at that point. So that's 6.633 radians per second. Hopefully that makes sense. And then, oh, okay. And then it's just a matter of putting that frequency, because that's the frequency at which the system would become unstable. That's relating to a... That's relating to this point here, or a phasor along that axis. So that's where our system would become unstable if our line was long enough. Yes, we're trying to work out how long that line can be. And it's quite easy to do that. We just put in the frequency at which that phasor crosses that point, that x-axis, negative x-axis, and then work out what length it is with a gain of 1. So with a gain of 1, it's 480, 1 over 480. So we could actually increase that k value, which we initially set as 1, to up to 480. Yeah, then you have 480 over 480, which would give you 1, which, going back to this, would then give us that point there. A phasor that would go from there right out to this point. Okay, I don't know how much you understood of that, but hopefully you can replay the video and follow it later on. Okay, so this is obviously a very stable system because we can increase the gain up to 480 before there's a problem, which is quite a big number. And that's just showing you the solution, yeah? So that's showing you that at this value of omega, the phasors along this axis here, there's just that little bit there. So we could actually make that much bigger. Okay. Right, Nichols charts are the third type of charts, and they're just a plot of gain and phase on the same diagram, so they're a little bit similar to the Bezier plots. They're actually quite easy to read, but they're not used very often. I'm not very sure why. I think in RF theory they're used more often. So there's only a couple of examples of Nichols charts. There's not much more to them than that. You've got gain in decibels on this side, or magnitude in decibels on that side. Phase in degrees on this side, and your key points are when the amplitude 0 or the magnitude 0 and the phase is minus 180. I can't see yet. So that little red cross there. So you can see that for the gain margin, you could shift the whole graph up by that amount. Yeah, does that make sense? Before it become unstable. And in terms of phase margin, here's the point where it crosses 0 decibels. So we could actually shift that whole graph back this much, from there to there, before it would cross minus 180 at 0 decibels. So I think they're quite easy to read. And you can see this is an unstable system because it's actually at minus 180, it's got positive gain of about 10 dBs or something like that. And at 0 decibels, it's got a phase shift of greater than minus 180, around about minus 200. I know the graphs aren't very clear. But again, this was done just using MATLAB. It's really easy to do again. Go into MATLAB, you can just type, what was that, Nichols? It's going to look a bit weird because it was just a weird diagram, but there you go. So that's one way of doing it. The other way of doing it is in Simulink, and I'll show you that too because you're probably going to be modelling your systems in Simulink. So with your coursework, what you have to do is you have to pick some frequency points. Probably the best ones to pick are probably 0, infinity, and any breakpoints that you have, so any poles or zeros, and work out by changing your S values to J omega. Let me write this down, it's probably easier. I can't remember what numbers it is in your coursework, it's right near the end. So by the time you get to the point in the coursework where you're at it, you're going to have a system GH equals transfer function. So you'll know what your transfer function is. Okay, so next thing you want to do is change all the S's to J omegas. Okay, then pick some frequencies. Of course, in radians per second, not hertz. So the ones I would suggest maybe certainly go for 0 to get your low frequency magnitude. The phase will be 0 there as well. Infinity, you obviously can't actually type infinity into your calculator, but you can, from what I've showed you, if you make omega infinity, then the amplitude becomes very small, goes down to 0, and you can check what your phase is. And then your breakpoints as well. So your breakpoints would be wherever your poles are, or wherever your zeros are. Now I can't remember whether your transfer function actually has poles and zeros. If it doesn't, just pick some frequencies. I don't know, maybe 1 radian per second, 10.1. You know, that would be enough. 3 frequencies would be enough, I think. Yeah. So that's if there's no poles. But there will be at least 1 pole. No matter how you model it, I think you'll have at least 1 pole or 0. Okay? So you just do that, and then you just do your calculation with omega in those values, and you'll end up with a magnitude and an angle, and then you can compare them to what you get on MATLAB, when you plot on MATLAB. So just to show you how to do it in Simulink, in fact, let's get you guys doing just an example, just to make sure you can do this. So, what did I type in MATLAB? Okay, so here I've got S plus 5 over S plus 4. Let's just do that. Nice easy one. We'll just get some reference. What was it?
Actually, what else? I want to ask. Maybe we take a person call. Oh, yeah, true. Good idea. Missed it as well, but it's such a Zoom camera and things. It's so stupid. No. I'm watching that.
Right, have a go at actually doing that just now. So following the steps I said, which was replace that with S with J omegas, and then just doing the maths calculations and complex theory. Do you all know how to use your calculators to change from rectangular to polar?
Yeah,
rectangular.
Most of the experts on
That's one thing I can do.
I suppose I better do this because I haven't actually done it.
This is going to take about 2 minutes to do this.
Pop down and get that.
Sure, welcome.
I'm going to look down and get a calculator. You'll be well doing this anyway, won't you?
Yeah.
5 minutes, maybe? 7 minutes? 5 to 7.
Rest of the meeting.
Why?
Oh, actually, that's bullshit.
That was in, it's still in October holidays, like, really short for all weeks. Why did you not tell us that?
Wasn't someone said the other thing? Was the scholarship shop 1 week in October? I was like, oh no, that does really well, eh?
It's Big Mark, what's the crack with him? Is he?
He's December. I'd rather do it in October than December, that's for sure.
Maybe November might be a shout, 'cause that's in holidays, like.
What's that?
That's in holidays, that's.
December? No, October.
It doesn't really care.
So I'd rather get there now than.
That's going to be a busy week at that. We're doing an Eve edition, and then we're doing the coursework. The coursework's going to be in
Robert.
I can't be done
Robert, why don't you hand this? Who was started?
Freshman's my word. Pressure. Okay, we'll go with
Make all the S's into zeros. The first thing you do. You got S to zeros.
You gotta tell me what it is.
We're going to
change the rectangular form. Is that what you do first of all?
We'll go with yes.
Eh?
Go with yes.
Ah, because she did it earlier. She changed it into rectangular form first of all, and then so you do S plus J.
Better ask Sue Wood.
No, that's right. That's wrong. That's pretty
Minus 4
No.
blue.
Here, better ask Sue.
Aye.
Mate, my head's mush, because that's a pole. That is a pole.
Well, if it's J 0, it's just going to be 0 straight.
Pole equals. And then your zero
So
equals.
when you just change,
Minus 5, correct. That is
zero,
from
just
that.
change S to zero. No.
Well, you'll have to, you would, for number 1, you would, because J times.
That's the
Imaginary number
W
is
equals
just
zero.
getting
So
I know, it's still going to be
what's
0.
what's a number for?
I mean, that has three.
What's the number?
Make it equals
Right.
0. You get rid of the X's.
Right. I'm saying.
Well, it's just W is great.
It has, so that's what
Omega.
I.
It's greater than infinity. It's impossible.
Or amplitude of phase.
It's falling big. Yeah.
Zero. That's fucking massive. Actually, yeah.
Just change that with zero.
Just 2, 5, 4.
Is that what you're doing now?
I think for number one, we're at 1.2.
Right, I'm going to just do the obvious.
I agree with that.
0 plus 5 over 0 plus 4. Can't do that.
Energy
Can I?
like your
It's better
20 ohm.
It's better than what we've got.
Ah, true enough.
Do you know what I mean?
Maybe
Just to rearrange it. So that's just going to be JW plus 5. J omega plus 5.
Yeah, have you done the 4 one already? I think make it minus 4. I think 4's not really going to work.
Oh,
Have you already done it?
No.
I actually thought we changed it.
no, last one, that's alright. I'm
It doesn't come out as minus 4 on the top, but I think you need to use minus 4 to do the
Yeah,
calculation.
don't do it. I wouldn't do that.
Right, see if I can get the answers.
It's just the biggest number you can do calculator, isn't it? Look.
They got one for penalty.
I'm not seeing that.
Zero.
Listen to me.
What?
Who do you guys know?
We'll listen.
Do you know it?
No, I don't know. I just go back.
How did you have one for?
Get back in March.
You have more this year?
That's a secret.
Or
That's a pure secret. Sorry, he's on here. Does it be the one?
nobody here wants it.
No.
I think you've done recording.
Not real, so.
Think she'll have a talk with him.
Hmm?
We're in the order.
Yeah.
We could put it in the notes again.
You get 45.
Yeah, that's not quite that far before.
No.
No, this is a rectangular number. So you need to make it into a polar form so that you can divide it.
1.25 angles.
No, I think we're right to the right actually. Shouldn't be. Fucking right through it.
Oh,
I don't know, because surely 0 times j, or just j zero, isn't it? J zero.
Probably not going to work, but we'll see what people get. Yeah. As long as you get the right answers.
Go bad yourself.
If you rewrite that first one will then be like this is 4 times j 0 plus 5 over j.
Ah, so.
Yeah, so it's a rectangular number, isn't it? So then the polar number is 0 and then 5. So you get 5. It's probably going to be safe. It's probably
but it's still 0 degrees.
Can you crack? Can you beef?
It's a wee bit different because it's got a whole under 0, which doesn't quite give me what I expected. Will I go over it? Yeah.
No, 2 seconds lost, please. That's all right.
Okay. Yeah.
Cheers.
A bit longer.
Thanks.
People manage it. You managed it, John.
What's that?
You managed to
Yeah.
do it. Yeah. It's just complex number arithmetic, really. It's not.
Oh, that's last year.
Even though it relates to.
Passed that last year.
Straight through last year.
It's great, man.
But you three people should be good at complex numbers. After doing electrical power.
Thanks, Lewis. We got a friend Manish, yeah?
But I don't remember the correct is it?
I'm going to show you the. Yeah, wait a minute, I'll show you the. So the 101. Go for it now, Lewis, if you want now.
Oh, right, so I'll carry on. Well, I'll do the omega equals 0 one first anyway. Okay, so omega equals 0, so we've got j omega plus 5 over j omega plus 4. If we make omegas equal 0, you just end up with 5 over 4. Yeah. Which I think equals 1.25, is that right?
You're right.
Okay, and then you probably want to, you might not have done this, but you probably would want to convert that to decimals, so you could plot that on your bode plot. So, strictly speaking, you probably want to do 20 log 10
Right.
of 1.25,
So it's 20 log 12.5.
which gives you 1.938 decibels. And what's the angle then?
0.
0, yeah, because there's no complex, there's no imaginary part, so it's got to be 0 to be. Okay? So, just leave it at that. Okay, that's quite easy. The second one's not exactly what I expected it to do, it's because there's a full and a 0. Does that make sense? Alright?
Sweet.
Okay, Robert, you okay? Yeah. Yeah. Okay, so the next one I said omega equals infinity was the next one, yeah? Obviously omega can't actually equal infinity, so omega tends to infinity. So we end up with j infinity over j infinity, which these bits disappear because they're small, which I think becomes 1. So that wasn't what I expected. I expected it to be 0 because all the previous examples I've shown you were 0. And again, that bottom term's got a, if you write that in complex form, you've got, in polar form, you've got alpha at plus infinity at 90 degrees divided by infinity at 90 degrees. So I think what you end up there with an angle of 0 as well. Yeah.
Result.
So 20 log 10 odd 1, that will actually give you 0 decimals. So that gives you 0, 0, which wasn't really what I expected, but it's because I gave you just a complete function that was just off the top of my head. Most of yours won't do that. Most of yours would tend to 0, not to 1. And then the fourth one, which is the more difficult bit. Has everybody done the fourth bit? Third bit, sorry. Remember the third bit?
Yeah, I'll show you how to do the third bit if you haven't managed that.
I can't do that first.
So for the third bit, we're going to make omega equal negative 4. If you did it with 4, it won't really matter. But okay, so then we're going to have minus 4j plus 5 over minus 4j plus 4. Okay, I didn't actually convert those, so does anyone want to tell me what they are in polar form? I didn't do it, I did it on my calculators.
6.4.
Sorry, 6.4?
Yeah. 128.66 degrees.
26?
128.66 degrees.
I think that's what I got.
Yeah, that's what I got. You never got it.
Well, I've just found out I did, but I didn't get that.
Right.
Just
I'll
gonna
do it
check
again
that
if you
again.
want, like. That's what I got it. There.
Didn't call you
I
no?
I just checked it.
So did you use minus 4? You did use minus 4, yeah?
That's right, yeah.
6.4. 2.
What you get for another one? 5.65.
5.65.
I get minus 38 degrees.
I think you're sitting wrong with your calculator though.
That's 6.4.
I got 120 as well.
I got
Sure,
2.5.
How did you do that?
Yeah.
Just minus 4,5.
I can't see how that could
Pole
possibly...
minus 4.
Polar.
Minus
Polar.
4, comma,
Yeah.
5.
I wonder why mine... Oh, mine's maybe doing it. Just trying to plot this in actual dimensions then. So we've got 5 across and minus 4 down.
Stay with the normal music, mate. We're just fucking arms out of this. Worst group example.
Okay, we'll go with what you've got. So I don't really understand
Yeah,
why.
we'll be right
Because
answer to this, that's all we.
I think it would be a minus number. Oh, right, okay. If I do 180 minus what was it? What you said? 100?
28.66.
128.66. Something over there.
Sorry,
It's going to give us about
No, even that doesn't work.
50.
Okay, we'll just go with what we've got. I don't know why my calculator's not in. What's the bottom line give us then?
5.66
Yeah.
and angle 135.
145.
No, that's...
That's right,
Angle 125. You've got different angles from me.
135. 135.
135, right.
Okay, I wonder why. It must be something to do with the trigonometry that's the angles are going wrong. Because I would have thought that would have been 45 degrees. But it must be the fact that that's negatives given us. Because normally that would be 45 degrees. Yeah, we've got 4 by 4 if it was like that.
Yeah.
It must be the fact it's negative. Okay, we'll go with what you've got then. Let's just carry on.
Mine would be better,
So then, if you divide those out, you've 6.4 divided by 5.66.
0.74.
0.74.
Oh,
You're lying, John. That's 1.5.
sorry. Sorry, Lewis.
There's something really wrong with his calculator. 1.13.
1.3 at an angle of...
Minus 6.34.
Just make sure you're switched on.
Oh, okay, so the angle came out the same as my answer. So,
We're on the same page then, though.
yeah, 6.3 or something
That's
like that.
6.3.
6.3? 6.4?
3.4, right?
3.4, yeah, okay. So the answer came out the same, so it must be... My calculator must have not taken into account the minus sign. I did type it in right, so... Right, okay, yeah, that's the right answer. And then, of course, you could change that to decibels, so you could plot it on your third plot. Okay, so folk who haven't done a lot of complex numbers hopefully do follow that.
Bush.
Right, what I was just going to quickly show you was how to do this in Simulink as well. And we're kind of running out of time, so this isn't going to take very long. Anybody got any questions about that? You okay with that? Did you do electrical power last year as well?
It's made a lot last
Yeah.
weeks. I still do.
Okay, so it's really only you three that haven't done a huge amount of complex number maths. But it's actually quite easy. Right. So we could plot that. In fact, we did plot that, didn't we? I wonder if we plotted that, whether it's going to show us the same thing. Maybe we won't bother doing that. What I want to do is go into Simulink.
There it could be.
So you can open the Simulink library with this sort of multicoloured window here. Have you all used Simulink?
What was it again?
Okay, let me do that again. Some people maybe haven't. Let's close that again. Okay, so it's easy to open Simulink from this window here.
What colour is that?
It's like a little coloured. It's the only coloured one on the
Blue,
bar.
white, and orange.
Red, white, blue.
I don't know what colour it is. Something red, white, and blue.
Did you choose red, white, and blue?
And then just choose a blank model. Just choose a blank model there. It opened a lot faster that time. Try and use 2018. Yesterday I found that I couldn't get 2018 on computers. So 2017 still works, but it's very, very slow. So try and use 2018 if you can. You can open the library through this window here. Again, multicoloured, red, white, and blue. No, white is red, white. And then down here is all your libraries. You can either use the libraries or you can also search in the window here. So for instance, if we want a transfer function, I can type that in. It's a bit small, you won't be able to see it, but and then hit return. I think that's going to take quite a long time. I'll cancel that because I know it's not really let me cancel it. That didn't even give us the right ones, actually, to be honest. But maybe it's because I never gave it time to finish searching. I know that my transfer functions are in the continuous block. It's this one here. It actually says 1 over s plus 1. I know it's a bit small. So you can left click and drag it onto your windows. And always, if you're doing this for reports, make sure I can see what's in the box, because I can actually zoom in on that. Maybe be able to see that a bit better now. But always make your boxes big enough that I can see the actual values in them, not just something that just says k ... which means the box is too small. So we want to change this transfer function. What was our one? S plus 5 over s plus 4.
S plus.
So if you double click on the box, you get a window like this. And the way it works from the highest power of s, and it adds the pluses and it adds all the s's to you, to the lowest power of s. So for instance, s plus 4, if we delete that, you need a square bracket, and then you need the multiplier of s. So if it's s plus 4, the multiplier of s is 1. 1 times s is s. And then, was it 5 or 4 on the top line? 5. Okay, and then the 5, and then a square bracket. And then the bottom line we had s plus 4, so all we need to do is actually change this second one there. And that should do it. So you can see I haven't put in any s's and I haven't put any plus signs in there. We'll do that automatically for you. Yeah, that should be our transfer function. And then if you want to do, I would say for Bezier plots, Nyquist plots, you're probably best using the analysis tool, but for step functions, you're probably better using the step and scope. I'll show you the step and scope first, because the first bit of your coursework, you're probably going to need the step and scope. So you've got the step in sources, and you just scroll down till you see it. It looks like a step, so there we go. Pop that in there. And then, I'm sure you've done this before, most of you will have. Sinks, you're going to use a scope. Okay, now the reason I say that you're probably better doing this with the step and scope is because you're probably going to need a transport lag delay. Because you remember with the Bitronic rig, we switched it on and there was a delay before it started to rise. So to properly simulate that, you're going to have to add in a delay. And that's really difficult to do. In fact, the control analysis tool just ignores delays, so it's not really going to show you a good representation. So just to show you that, I'm going to add in the transport delay. Can't remember where that is, so I'm actually going to have to search for that. This, of course, isn't the right function. That's not the right transfer function for your system. That's just one I made up. Don't everybody hand me in reports with this transfer function. That would be definitely wrong. Finding the transport delay. So I'm just waiting for it to come. Quite slow. Yeah, so there, transport delay. You can add that in, that'll give you your lag time. Yes, I'm not saying this is what your model will actually look like, but just to give you an example. Okay, then up in here, this box here, it's a bit small, but that's the amount of time that you're going to simulate for. Is 10 seconds long enough for your system? Long enough for this system. Is it long enough for your Bytronic model? No, it's nowhere near long enough. I think it took about 200 seconds to go up. So you probably want to simulate for a longer time. You just type in your time you want to simulate and then click the green button and it will run. There's a little thing down here that should tell you it's running. See that? That actually didn't take very long. And then you can look at your scope. Hopefully. I don't know why I did it. Okay, you probably can't see that very well, but you can.
Change it to white, can you not?
You can change it to white. If you go into style,
Should see it green now.
for some reason it's axis colours. I don't really understand why. But that change. And if you want to change the outside bits, that's the other selection. So you can see there that this is what this particular transfer function has done over that time. You can zoom in and things as well. There's a zoom tool here. No, sorry, that's not the zoom tool. There's a zoom tool here. You can zoom in the x-axis or the y-axis or the total plot. So I want to zoom in the x-axis, I can just do that. Yeah, if you get the idea. If you want to turn that off, you have to click it again, which isn't that intuitive, but that does that. So that's fine for doing your time step type functions. If you want to do your frequency analysis, which is the stuff we were looking at today, and what you're actually better with is adding an input and an output. Or in fact, I wonder if you can do it this way. Depending on the version of Simulink you've got, you can add in linear analysis points instead. So I'll just show you doing that. So this would be an input point. So what I've just ticked there was input perturbation. Perturbation, that's a long word, but and then an output point, linear analysis points, output measurement. So this is only newer versions of MATLAB and Simulink do this. The old ones you had to add a source, which was an input, and a sink, which was an output. Just show you those as well. So this little block here is an input, and then that block there's an output. So you'd have to replace the step and the scope with those instead, if you've got an older version of Simulink. But if you've got a newer version, you can add these points in, and then you can do analysis, control design, linear analysis. Takes a wee while to run. Okay, if you've used inputs and outputs, you'll have to change that little box there to say root level inputs and outputs. Okay, but because we haven't done, we've just used it model IOs. I think we can leave it at that. And then, of course, you can use, there's all your graphs there, Bode, Nyquist, Nichols. So go with the Bode one, I think. I've never actually done this with inputs and outputs. We'll see what it works. Looks like it's working. Yeah, so there's our Nyquist. Sorry, our Bode plot for this circuit. Or this transfer function. And actually, you can see our infinity pointer is right enough, yeah? Our phase is tending to 0, and our gain is tending to 0 decibels. And that looks about right for our low frequency as well. Worked out about, what, 1.8 or something? That's quite close. Yeah, so, and you could check what it was at the other frequencies as well. If you want to plot these, you have to go into plots and results, I think. I'm sorry, no, that's wrong. Oh, Bode plot 1. And then that's a print to figure type of diagram. Of course, you can just do all print screen as well, that would still be okay. But you do. Okay, so now you can probably do the first few bits of your coursework and the last 2 sections. The only bit I haven't showed you is the bit about the controllers, which we'll do when I come back. But you can have a look at what we did last year on controllers, and I think you'll pick it up because it's PID controllers, which you've used before. Yeah?
Magic.
So that's all for today. So no class next week, although you can still come in. But do sign in downstairs. Any questions about any of that? You did quite well. I thought you did the calculation well, some of you. Not that easy, this day. Just get on with your coursework now. There will be some questions from this week's lecture as well, in the self-assessment question section. There always are. So you can choose to do them, or you can do your coursework.
a 5-minute break.
Or you can have a break.
This call has been disconnected. Thank you for joining.